Today we're going to continue our look at the second part of modern physics, and that's quantum theory. And I've subtitled this lesson, How Weird is the Universe? Because you're going to see that the implications of quantum theory is that the universe is very, very weird. So last time we saw that physicists had accumulated a overwhelming amount of empirical or observational evidence, including the diffraction of light, the different colors of light, and Young's double slit experiment with light performed in 1801, that light has to be thought of as a wave. And this was put together in a complete explanation of electromagnetic radiation by James Clerk Maxwell in 1867. But then we saw that going from there, physicists also accumulated an overwhelming amount of observational evidence, including black body radiation, the existence of spectral lines, and the details of the photoelectric effect, that light has to be considered not a wave, but a particle. And that was the beginning of quantum theory with Max Planck in 1900. The only way to reconcile all of these observations that seem to contradict one another and these theoretical explanations that both seem to work is to accept the idea of the wave-particle duality of light. That light is something beyond our everyday experience that has both wave properties and particle properties. We went on to see that in the 1920s, things got even weirder because observational evidence, such as repeating the Young's double slit experiment, but with beams of electrons rather than light, demonstrated that matter also exhibits wave-particle duality. Now that at first seems ridiculous because we're very familiar with matter and we don't see it waving. But we now understand that the reason we don't is because the waving effect, the wave properties of matter, only become evident at the tiniest scales of the universe, down in the level of subatomic particles, what we can refer to as quantum scales. And that's because of a constant that is built into the universe, what we now call Planck's constant, and it's very, very small, 6.626 times 10 to the negative 34 joule seconds. If this value were bigger, then the wavelengths of matter would get longer and we would see them at larger scales. But we have to accept the idea that at quantum scales, reality is both particles, meaning that the reality is bits of matter that are localized in space. They have a single particular location that we can talk about, and they're characterized by mass, the amount of matter they contain. But the same objects at the smallest scales also have to be considered have properties of waves, meaning that they're not matter, they're motion. They're not in one particular spot in space, they're delocalized over a large region of space. And they're not characterized by mass, which is the amount of stuff, they're characterized by wavelength, which is the length of the motion. This seems to be contradictory. We looked at an analogy though, and all the observational evidence and all our rational thought about it suggests that this is actually real. However, it also means that there are some pretty major implications for the nature of reality, and that's what we're going to look at in this lesson.